Now, if you have any questions later on during the sessions, please just type in the chat, okay? Or if you can raise your hand also so that I can notice I might mislook the chat. Raise your hand and then type in the chat, okay? So these sessions will be recorded. Then I will share this later on the YouTube. So the first thing is, as I mentioned, read the questions carefully, and that is for you to know what are required by the questions. Because, as I mentioned, time is limited. If you write those which are not needed, you might lose time. You write those which are not needed might be because you don't understand the questions, okay? Now, the second thing that I would like to mention first is the things that I have gone through, then things that you are expected to know, and things that you will be writing coverage in the exam on my part, okay? So my topics, okay, that I will ask in the questions in the exam will be first, it is theory of elasticity. Now, class, if you can't see, if I write in the place that you can't see, please let me know, or if the voice is not clear, please let me know by the chat, okay? Then the second one is I will also set question for the use of energy method. Okay. So these are the topics that will be parts of the coverage of the exam. And the other one, of course, you have from Prof. Taxia. This is my part, and then the one that from Prof. Taxia will be finite element method. Okay. So these are the topics that we cover that you expected to know and will be tested in the exam. So I will cover mainly on theory of elasticity, then I'll also touch on energy method. So briefly, I'm not able to cover everything in detail, but I will give you a refresh what we have covered and what you're expected to know. Now let me start with theory of elasticity. So let me start with theory of elasticity. What are the things that we have covered so that you can recall? Those are the things that you're expected to know. So theory of elasticity is a field that we use to solve a problem, an elastic body under the action of forces. And the body can be any shape, and we want to know the stress, strain, and displacement. Okay? So under theory of elasticity, you are exposed to what is the basic equations. Namely the equilibrium, stress, strain, and strain displacement relations, which normally represent compatibility. So the three basic ones. Okay? Equilibrium, stress, strain, and compatibility, or we represent it in the strain displacement relation. So these are the three basic relations that you need to know. And then also we cover what are the variables. The variables that we need to solve, it will be displacement, in general we have 3, stress, we have 6 because of symmetry, and the corresponding strain you have also 6. Equilibrium equations, you have 3. Stress-strain relation, you have 6. Strain displacement relation, you have 6. So these are just to refresh you, we have covered this. So the variables that we need to solve in using theory of elasticity by using these 3 equations is displacement, stress, and strain. Of course, this one is not enough. You have to plus with the boundary conditions. Okay, if you can't hear, okay. All right, there's a question here now. Okay. Okay, so I will come to that, how to derive that thing. I will come to that. Let me go through first, give you an overall refresh first on these things. Okay. So plus boundary conditions, and then you have 2 boundary conditions, which is the geometric boundary condition and the natural boundary conditions, or the stress boundary conditions, or the displacement boundary conditions, or the kinematic boundary conditions. So these are first in theory of elasticity, and we talk about what are the stresses, what about the strain, and 3 normal stress, 3 shearing stress, and altogether you get 6 stress and 6 strain, and 3 displacement in X, Y, and Z coordinate directions. So the next thing that I covered is on the derivations. Of course, how to derive all the equations, how to derive the equilibrium equations using a infinitesimal volume inside a general elastic body. And when you are given a elasticity problem, when you're talking about stress and strain component class, it is very important you take note of the coordinate system. So the coordinate system that we use to define the direction of the stress component X, Y, and Z, you must state clearly when you answer the questions and take note of whatever coordinate system given to you. Okay. So that is the overall things that I cover on theory of elasticity. Then we specialize, we go for specializations. All these are used for in general 3D, but when we want to apply it to structural problems, we look at the particular shape, the loading, then we specialize them. So we specialize these. The next thing is I cover on specializations. Okay. Specialization to 2D problem and also 1D problem. So 2D problems, further, you have the main one that we cover will be the plane stress. So the condition of plane stress, you have to know for what are the situations that you can classify as plane stress, plane strain, okay, what are the conditions that you can classify the problem as plane strain, and the corresponding variables and the corresponding variables that we need to solve, unknown variables that we need to solve, and also the corresponding equations. Then we have axis symmetrical problem. So these are typical 2D problems. And then 1D is the basic, the bar problem. Okay. So these are the things that mainly overall I cover in 4 weeks of theory of elasticity. And to give you an overall things in mind, I think these are the things that when you talk about 2D problem, 1D problem, plane stress, plane strains, then you must be clear in your mind what it is about, okay? Under what conditions we classify plane stress, plane strain. And 1D problems, so 1D problems, what are the characteristics of the 1D problem? So these are the things that start out with this to give you some idea, okay? Later there is a question, how to derive, then I go into more specific in the next session. Okay. Now, these are overall things on theory of elasticity. Okay. So next, I would like to go a little bit more on stress and strain, which are important for us to define. Will be the, whenever we talk about stress and strain components, it is very important the coordinate system must be shown. Whenever you have an infinitesimal volume, so the coordinate system given or the coordinate system not given, when you want to answer, you want to explain, you must state clearly the coordinate system, which is x positive, which is y positive, which is z positive, so that you can define clearly what is sigma x, okay, what is sigma z, where is sigma y, and the corresponding tau xz, tau zx, okay, and the corresponding tau y z and tau zy. So those are the things, and here of course we have tau x y, tau y x. So this xy, it must be the xy and xy, the meaning xyz must be given clearly in any answer. Okay, the questions given also, they must refer clearly to the xyz. So coordinate system is important to indicate. Okay. Now, we have stress component, okay, and 3 normal stress, and the other one is 3 shearing stress. And from rotational symmetry, we get interchange the superscript, they are equal. So we have 6, altogether we have 6, and the corresponding strain. Corresponding to normal stress, we have normal strain, and corresponding to shear stress, we have the corresponding shearing strain. And they are symmetry. So stress component, strain component. So now these are the unknown variables that we want to solve in the problem, okay? And we have the basic equations. So, but stress, these are stress components. So stress is a kind of tensor. Stress is a tensor quantity. Strain also tensor. And when we want to represent what happened at a particular point when an elastic body is being stressed, so we represent them using the stress component. And the state of stress at that particular point, if it is mentioned state of stress at a particular point, meaning that we need to state of stress at a particular point, meaning that we have to give the stress tensor and then show the component in terms of this x, y, and z coordinate. So you have sigma x, you have tau xy, tau xz, then you have this tau zx and xz, they are the same. Okay, then you have the tau xz, tau yz and sigma z. So state of stress is representing using stress tensor in this way by arranging the component in the matrix form. Okay. So that is called state of stress. In the same way, we have state of strain. Okay. I hope the writing is large enough. Later, you can see from the screen, and when I share the video, you can see the writing. Okay. State of strain also, if state of strain is represented also by strain tensor, and it will be epsilon x. And this one will be, we use epsilon xy, epsilon xz, epsilon xy, epsilon y, epsilon yz, same, epsilon xz, epsilon yz, epsilon z. But when we are asked to state what is the state of strain, these are the things similar to state of stress. You have to show the tensor, and in component form represented in matrix like this, and referring to this coordinate system. And the component of this shearing strain component, we must be careful. This one is equal to half gamma xy, half of gamma yz, and similarly half of gamma xz. So when we want to express in state of strain, we must use strain tensor and the component of strain tensor and the relation with the component of engineering strain here is given by that relationship. So after we evaluate this value, for example, then we have to multiply with half to get the strain tensor component for the shearing part, the shearing strain part. The same thing for this, there must be a half, there must be a half. So some of the assignment that I've given to you, I think some of you are not careful with the relations between strain tensor and also the engineering strain. So I would like to remind you there is a relations between engineering shearing strain. This is we call the gamma engineering shearing strain, and the strain tensor component, where there is a factor of half here to relate to the strain tensor component. Okay? So these are one of the few things that I would like to make it clear to you all. And the next thing that I would like to talk about is on the stress-strain relations. Okay? Stress-strain relations relating the 6 stress to 6 strain in general 3D. And when we go to specializations, so the stress-strain relationship are being reduced because the number of stress, non-zero stresses in 2D is less than 6, in 1D is only 1, so the corresponding stress-strain relationship also reduce. Okay? And I would like to next touch on that part, okay? Between stress and strain. So let me erase this. So this is recorded. Later you can refer. Okay. So stress and strain are one of the basic relations that we need to solve completely the structural problem. So stress and strain in general 3D, and if you are talking of homogeneous isotropic body, so the only two material properties that we need to know is this, and the shear modulus, there's a relationship for isotropic. There's a relationship between the shear modulus G with the Young's modulus. So these basic relations, you should know how many is the independent material properties that you need. Okay. So normally we can write down the stress-strain relations in this way. So this sigma x, because of the 3D effect, you have Poisson ratio. And in the same way, you have the second relation. So you may start with this plus the direct effect of sigma y to the strain plus the Poisson ratio effect, the 3D effect. Whatever you stress in one direction, you're going to cause strain in that direction, and the direction perpendicular to x or y, you have also the strain. You have also the effect caused by that particular stress. Then sigma z will be plus sigma z over E. So whatever happened in other directions perpendicular to z will also cause strain in that direction, but in the negative directions. So positive y will cause negative strain in z direction. Positive sigma x will cause negative strain in z directions for this case, and for other case also, we have this Poisson ratio effect. Then for gamma xy, it is tau xy divided by Poisson ratio, shear modulus, gamma xz, tau xz divided by G, gamma yz divided by G. And don't forget, G is related to E by these equations. So these are the basic equations that you need to know. Okay? Okay, so this is strain. Okay. Of course, the definition of strain, of normal strain, is change in length of an element in x directions divided by the original length, is this, and the same way for y and z. Gamma xy, gamma xz, and gamma yz. If you talk about distortion of an original shape, which is 90 degrees, which have an edge of 90 degrees to each other in xy, but after that, there's a change in angle of change in angle that happen in xy plane, in xz plane, in yz plane. Okay? So those are the basic stress-strain relations. And what is important that we need to relate this stress and strain to is, now, this strain is equal to change in length over original length. For example, change in length, if it is x, change in length in x directions divided by original length in x directions. So the same thing for epsilon y and epsilon z. So this is change in length, and there is divided by original length, there is no unit for that. And so if we get the strain, and if we want to know the change in length, then we must multiply change in length must epsilon x multiplied with the original length in x direction. For example, if it is given as dx, the original length can also be x. Original length of one problem given to us in x direction can be a, for example. So you have to multiply with the original length to get the change in length. So this epsilon x itself is not change in length. It's a relative change in length. Change in length divided by original length. So if we are asked to determine change in length, we have to multiply by the length of a particular element in x direction itself. And if we are asked to find what is the deformed length, or length of the element after deformation, so that should be a plus change in length, or a1 plus epsilon x. So this is deformed length in x directions, for example. So deform length in y directions, it has to be whatever direction original in y directions multiplied with 1 plus epsilon y. And if it is deform length in z direction, it will be whatever length, original length of an element in z direction. Let's say it is c or dz multiplied with 1 plus epsilon z. 1 plus epsilon z. Okay. So that is a few of the terms that you must be able to relate to this epsilon here. Okay. So this epsilon. So those are the things that we can make use of this to find. Change in length have to multiply with the original length. Deform length, you have to add the change in length to the original length, then only you get the deformed length. Okay. So those are some of the important things that we have to take note. And remember, stress or strain has no unit. Okay? And length, of course, it depends. Our unit can be millimeter, meter, depending on what is given to us and in which unit we want to express that length in. Okay? So in this respect, I want you to take note of the unit that you must use consistently. If stress is in megapascal, then the E and G also must be in megapascal. Okay. And don't forget, to get the strain, you need to divide with the E, so they must be of the same unit. So if E is given as 200 gigapascal, this is not the same as mega, so we have to change to megapascal. Then only we divide megapascal, then we get the correct unit. The unit that we divide must be consistent so that at the end we get the correct value for strain. Now, strain value normally is very small, 10 to the power of -4, 10 to the power of -5. So if you calculate your strain to be 100, 200, or 400, that means something wrong. Either you forget to divide with the E, or the unit you forget to convert into the correct unit. So strain are normally very small value. Okay? These are small value. So if you calculate your strain to be 200, 2000, then you should realize that something wrong with your calculations. Either, as I mentioned, you forget to divide with the E, or the conversions of the unit is not correct, then you get unreasonably large value for stress and strain. Okay. So this is something about stress and strain that I would like to talk about. Okay. Now let me pause here for a while to see if you have any questions so far before I go to the next one when I talk about specializations.